our class on fundamental math for solar applications, where we're going to take the things that we just learned and we're going to apply them to some real-world examples from the PV industry. First, we're going to calculate the effect of temperature on our open circuit voltage of our module. We know that our modules will produce a certain amount of voltage at the standard test condition temperature of 25 degrees C. And for every degree we go below 25 degrees C, that voltage is going to go up a certain percentage, and that's a set ratio for the module. It will also go down if we go above 25 degrees C, but right now we're focusing on what happens when the module temperature goes below 25 degrees C. We have a sample of a specification sheet for a module here. We have a minimum temperature from our location of negative 19 degrees C. That's for the specific spot that this module is going to be installed. The first thing we need to do is calculate the difference in temperature between the standard test condition temperature of 25 degrees C and the low temperature that we experience on the site. In this case, we're going to take negative 19 degrees C and subtract 25 degrees C, that's our standard test condition temperature, to get negative 44 degrees C. Now keep in mind that this is not the temperature, negative 44. This is the difference between 25 degrees C standard test conditions and the minimum temperature on our site. So there's 44 degrees difference between standard test conditions and the minimum temperature on that site. From there, we can calculate how much the voltage is going to change due to this difference in temperature, which is also referred to as the delta T. That's the triangle symbol is delta, and that indicates a change in temperature. And we can calculate this by multiplying the delta T, the change in temperature, negative 44 degrees Celsius, by the temperature coefficient of open circuit voltage, which they give us right on the module specification sheet. In this case, it's negative 0.29% per degree C. So if we multiply negative 44 degrees C by negative 0.29% per degree C, we get 12.76%. Now, in this calculation, the two temperature labels, the one on negative 44 and the one on negative 0.29, cancel each other out, and the negatives also cancel each other out. You know, two negatives make a positive. So we have a positive 12.76%, which is what we want because we know as the temperature goes down, the voltage is going to increase because there's less resistance internally in the module, so the module is a little more efficient. So we can convert this 12.76% to a decimal by moving the decimal place over to the left 2 positions. So the decimal equivalent of 12.76% would be 0.1276, which is what we will use to calculate the actual voltage of this module in the next slide. Because we don't want the percentage, we want to know what the actual voltage is. So in order to get that, we need to convert the percentage to a decimal first. Okay, let's take a look at how we calculate the temperature-corrected maximum module voltage. We see the formula at the top in the green box. I'll read it out to you and let you know what everything is. It's the open circuit voltage, which we get from the specifications sheet. Then we multiply that by the product of 100% plus the T min, which is the minimum temperature. We know that was negative 19 degrees C from our last slide. The temperature at standard test conditions, we know that is always 25 degrees C, and we multiply that by the temperature coefficient of open circuit voltage, which we will also get from the specifications sheet. So if we fill our data in, go to the specifications sheet, we can see our open circuit voltage is 40.5 volts. Put that into the formula. 100% is always there. We know that our site has a negative 19 degrees C minimum temperature, and that's going to vary depending on where you're located. Standard test conditions are always the same, 25 degrees C. And we go to the specification sheet again to get the temperature coefficient of open circuit voltage, in this case negative 0.29% per degree C. Now we just follow our order of operations. We know PEMDAS. We're going to start with the parentheses and do everything in the parentheses first. And since this formula has multiple sets of parentheses, we're always going to start with the center one, the one that's at the middle. This one is the negative 19 degrees C minus 25 degrees C. So if we do that calculation, we get negative 44 degrees C like we saw in the last slide. Then we'll stay with the innermost brackets, which are the negative 44 degrees C multiplied by the negative 0.29% per degree C, which we also saw in the last slide, gives us 12.76%. Finally, we're on our last set of brackets, 100% plus 12.76%. Now here we can choose to either add those two together to get 112.76%, or we can convert to a decimal here by moving 2 places to the left. So the 100% becomes 1, 12.76% becomes 0.1276. And then we can add together there. Either way, we're going to end up with 1.1276. And that's what we're going to use to multiply by 40.5 volts to give us our final result of the increase in voltage that we'll see for temperatures below standard test conditions. In this case, the voltage will go up a little more than 5 volts to 45.76 volts. And that is the temperature corrected maximum module open circuit voltage. So here we've done a bunch of things. We've used our orders of operation, we've subtracted negative numbers, we've converted from a percent to a decimal, and that is all the things that we needed here to get to our temperature corrected maximum module voltage. We did not have any exponents here, so we didn't have to do those. We would have done those after we did the parentheses, but there were no exponents in this example, so we just skipped that and went right to multiplication and division. There was no addition and subtraction in this formula either. So we only had to use a couple of our orders of operations to finish this question off. Now let's calculate the watts per square foot of a module. The first thing we need to do is make sure that we're using the right unit of measurement to get the watts per square foot. So we need the square foot measurements of the module. This module manufacturer gives us the module dimensions in either millimeters or inches. But I don't want watts per square inch, I want watts per square foot. So first I need to convert the inches to feet. I know that there's 12 inches in a foot, so I can take the inch measurements that the manufacturer gives us and divide by 12 to get the equivalent number of feet. In this case, 83.38 inches divided by 12 inches per foot, and we get 6.95 feet. I also take the width, 41.33 inches, divide by 12 inches per foot, and get 3.44 feet. So now I've got the dimensions in feet, which is the proper unit to get watts per square foot. Next, I need to calculate the area of the module, and we know that since the module is a rectangle, we just multiply the width times the height to get the area. So the 6.95 feet times 3.44 feet gives us 23.9 square feet. That's the unit of measurement that we need to calculate watts per square feet. The final step, we take the wattage of the module, they've given us the power at standard test conditions, 435 watts, divided by the area of the module, 23.9 square feet, to give us 18.2 watts per square foot. This is division, so we have to make sure we do the order properly. We want watts per square foot. Watts come first, square foot comes second, and that will give me the right answer. If I did it with the area first and then the power, I'd have feet per watt, which is not a metric that we use in the solar industry, but it would be a very different number than what we got in this calculation. Now we're going to calculate the array output based on the irradiance. We know our standard test condition irradiance is 1,000 watts per meter squared, but our array is not usually working at 1,000 watts per meter squared. It's actually quite uncommon for us to have exactly 1,000 watts per meter squared. So if we want to estimate how much a PV array could produce at a different irradiance level, we need to calculate a factor out and then calculate what the expected irradiance is. So in this case, we have a 5,200 watt PV array. The irradiance that is currently being measured at the site is 750 watts per meter squared. The first thing we need to do is calculate our irradiance factor, and we do that simply by dividing the measured irradiance by the standard test condition irradiance. So 750 watts per meter square divided by 1,000 watts per meter square gives us a 0.75 irradiance factor. And this is why we like using the 1,000 watts per meter square, because it's super easy. Whatever the irradiance is, just move the decimal over 3 places and you've got your irradiance factor. So 750, easy, move it over 3 places and you get 0.75. If it was 600, move it over 3 places and you get 0.6, or you'd have 60% of the standard test condition irradiance. If it was 1,200 watts per meter square, you'd still move it over 3 places and you get a 1.2 irradiance factor, because the irradiance would be greater than standard test conditions. It would be 120%. So we can take that irradiance factor, multiply that by the size of the array. We know we have a 0.75 irradiance factor with a 5,200 watt array. If we do that calculation, it comes out to 3,900 watts. Now, this doesn't take into factor a lot of different things that go into array output. So shading, cell temperature, inverter inefficiencies, voltage drop, module mismatch, soiling, all kinds of things like that would also reduce the output of the array. But for this simple calculation, we're just going to figure out what impact the irradiance alone has on the array. If we took that same array, what would it produce at 330 watts per meter squared? It's the same formulas. We take 330 divided by 1,000 watts per meter squared, get a 0.33 irradiance factor. It's 33% of the standard test condition irradiance. Multiply that by 520 watts and we get 1,716 watts. That's our expected output, not taking other factors into consideration. And I will say that irradiance has the largest impact on array performance. So if you're on a site and need to do a down and dirty estimate to see if your array is producing what it should be, you can take the irradiance using a irradiance meter and then figure out what the irradiance is, divide that by 1,000, get your irradiance factor, and then multiply that by the size of the array, and you'll get an approximate output. It's not going to be exact, but it will give you at least an idea of whether the array is producing close to what it should be. Okay, let's calculate the area of this triangular roof. We know that the formula for calculating area is base times the height divided by 2. So in this case, our base, the width of the base of the triangle, is 24.75 feet. The height, which again is not the length of the top of the triangle there, it's the vertical height from the edge of the base up to the peak of the triangle, and that's 17.3 feet. We multiply those two together to get 428.2 square feet, and then we'll divide by 2 to get an area of 214.1 feet. Keep in mind our orders of operation, PEMDAS, we're going to start with parentheses, there aren't any. Then we'll move to exponents. Also, there aren't any exponents, so we'll go to multiplication and division. Since there are both multiplication and division in this formula, we start from the left and move to the right. So we do the 17.3 times 24.75 first, get the product of that calculation, and then divide that by 2 to get our answer. Now finally, let's look at how we calculate the minimum overcurrent protection device size. That's our minimum breaker for an inverter. National Electrical Code says our minimum breaker or fuse size, that's our overcurrent protection device, must be 125% of the rated AC continuous output current of our inverter. If we look at our specifications sheet for this 7,600 watt inverter, the maximum continuous output current at 240 volts is 32 amps. We convert the percent to a decimal, so we move the decimal place to the left 2 positions, and we get 32 amps times 1.25 gives us a minimum overcurrent protection device size of 40 amps. Very standard calculation. We do this a lot in solar to see what the output of our inverter is and then match that to the proper overcurrent protection device size. This will ensure that the breaker doesn't nuisance trip, because this inverter is operating at what they consider continuous current. It's operating at maximum current potentially for 3 hours or more. So this is how we size a breaker. Simple application. We had to multiply, we had to convert that percentage to a decimal, and then come up with our answer for our breaker size. That's the end of our course on fundamental math for solar applications. We hope that this helped you brush up on your math skills that we will use in almost all of our courses in one way or another. So good luck with your future in the solar industry, and we hope you join us for another class. Thank you very much.